So here we have a situation dealing with a slingshot. So the slingshot is stretched back 18 centimeters. A ball of mass 65 grams is placed in the slingshot. When the ball is fired, it leaves the slingshot traveling at a speed of 14.25 meters per second at a height of 1.88 meters above the ground. We want to calculate the spring constant in A and then the speed when the ball reaches the ground in B. So we have a lot of given information. So let's start by drawing a diagram. So here's our slingshot. Okay, use your imagination a little bit on that. So here is the elastic band that we stretch back, and this is stretched 18 centimeters back. The ball is fired. At 14.25 meters per second. And we have the ground in here, so the ball travels on and reaches the ground over here somewhere. That ground is 1.88 meters below the level of all this original stuff. And then we also know the mass of the ball, 65 grams. In part A, we want to calculate the spring constant of the slingshot. Well, spring constant, we've got in Hooke's law, F equals Kx, or from the slope of the graph, change in force over change in position. But when we try to use these equations, we run into a problem. We don't know anything about the force that's being used to be able to pull that slingshot back. So neither one of these is going to apply. However, the situation we have is one that is governed by elastic forces here and gravitational forces there, in which case both of those are conservative forces. Mechanical energy stays constant. So then the mechanical energy, when we stretch the slingshot back, those joules are going to match the mechanical energy when the ball is fired, and for that matter, that's going to match the mechanical energy when the ball reaches the ground the instant before it hits the ground. So we can use this to be able to calculate what our spring constant is. We know enough to use the stretched segment and the fired segment. Remember our three all-important questions. MHS. Is anything moving? Is anything raised to a height? Is anything stretched or compressed? So, when we ask those questions about the initial instant, moving, no, the ball's not moving when it's stretched back. Raised to a height, the height doesn't change from the moving to the fired, so that would be a no. Stretched, yes. So the only thing we fill in here is a 1/2 kx squared. Asking the same three questions about the fired, the only thing we answer yes to is the 1/2 mv squared. So then filling in values, I do have a 1/2 on both of these. It will divide out. And so k multiplied by x, that's the amount of stretch, converted to meters, 0.18 meters squared, equals the mass converted from grams to kilograms, 0.065 kilograms, and then V, 14.25 meters per second, quantity squared. When we solve this down for the spring constant, we get a value of 407.38 newtons per meter. Now, part B, calculate the speed of the ball when it reaches the ground. Well, now we're going from the fired over to the ground, the instant before it strikes. That's being governed by gravity, which is also a conservative force. So then we have to use the ground section. We can use either of these two sections. It doesn't make any difference. I'm going to go with the fired section and the ground section. So mechanical energy when the ball is fired. is equal to the mechanical energy when it just reaches the ground before striking. Asking our three questions, MHS, moving, fired, yes. Raised to a height. Now, the height is going to come into play in this part. So then the height changes before we get to that final location. So I will also have an mgy here. So 1/2 mv squared for the moving and mgy for the height. When we reach the ground, nothing's moving or nothing's raised to a height. Nothing is stretched or compressed in either one of these instances. So the only thing we have is a 1/2 mv squared. And this velocity is the velocity when it reaches the ground. That's the one we're trying to find. Now, in this calculation, I have an m there and one here and one here. You can divide the whole equation by mass and it will divide out. And that's what I'm going to do. So then 1/2 times the velocity when it's fired, 14.25 meters per second squared, plus gravity 9.8 meters per second squared, multiplied by y, that's the 1.88 meters, equals 1/2 times the velocity at the ground squared. Doing your algebra and solving down for that velocity, we get the velocity at the ground is 15.49 meters per second. Now, one note, this is really a speed, not a velocity, because when the ball reaches here, it will be traveling at some downward angle. So the number we calculated here is not a horizontal, it's not a vertical, it's at combined diagonal. Since we don't have a direction, this is really a speed, not truly a velocity. Ponder physics.